What if the secret to time travel has been lurking at the heart of the universe all along? Imagine a place where the laws of physics are torn apart, where time itself can twist, bend, and maybe, just maybe, loop back on itself. Welcome to the world of black holes, the most mysterious objects in existence. In this journey, we'll go beyond science fiction and into the most extreme reality ever discovered. We'll see how black holes could hold the key, not only to understanding the universe, but to unlocking time travel itself. You'll learn why black holes fascinate scientists and dreamers alike, how they're created, what happens if you fall into one, and why they may be the only real ticket to the past or the future. If you're curious, passionate, or just love a great cosmic mystery, hit that subscribe button and get ready to have your mind blown. Let's start at the beginning. What is a black hole? It's not a hole in the traditional sense, and it's certainly not empty. A black hole is a place in space where gravity has become so powerful, nothing, not even light, can escape. To understand why, imagine squeezing a star many times bigger than our sun into a space smaller than a city. The result is a singularity, a point of infinite density, surrounded by a boundary called the event horizon. The event horizon is like the edge of a cosmic waterfall. If you drift close enough, the pull of gravity becomes inescapable, dragging you toward the center faster and faster, until even light cannot escape. From the outside, a black hole is invisible. We see only the swirling disk of hot matter that spirals in, heating up and releasing X-rays just before vanishing forever. Black holes come in different sizes. Some are only a few times heavier than the sun, born from the collapse of massive stars at the end of their lives. Others are millions or even billions of times heavier, lurking at the heart of nearly every galaxy. The biggest ones, supermassive black holes, are so enormous they could swallow entire solar systems. But here's where things get truly wild. According to Einstein's theory of general relativity, black holes don't just curve space, they also distort time. Near the event horizon, time slows down dramatically compared to the rest of the universe. This is more than a sci-fi plot twist. It's a real, measured effect, confirmed by experiments and astronomical observations. In fact, time dilation has been tested on Earth. Atomic clocks placed at the top and bottom of tall buildings tick at slightly different speeds. So, what does this mean for time travel? Imagine you had the technology to hover just outside a black hole's event horizon. For you, a few minutes might pass, but for the outside world, years or even centuries could fly by. Leave, and you've effectively leaped into the future. This time shift effect, while extreme near black holes, actually exists everywhere in the universe, though on a much smaller scale. Gravity bends time, just as it bends space. But what about going backward in time? That's where the true secrets of black holes begin to emerge, and where physics starts to brush up against the impossible. The idea that black holes could be gateways to other times or places comes from some of the wildest solutions to Einstein's equations. The math allows for strange possibilities: wormholes, closed time-like curves, and white holes, theoretical opposites of black holes that spew matter out instead of pulling it in. Could black holes really connect distant parts of the universe, or even create shortcuts through time? Most physicists are cautious, but the questions refuse to go away. Some of the world's greatest minds, Stephen Hawking, Kip Thorne, Roger Penrose, have devoted their lives to exploring these cosmic riddles. And with every new observation, from gravitational waves to the first ever image of a black hole's shadow, the mystery only deepens. To really grasp what's at stake, picture this. If you fell toward a black hole, someone watching from a safe distance would see you slow down, freeze, and fade away. For you, time would feel normal, but as you crossed the event horizon, the rest of the universe would seem to rush forward at impossible speed. In a sense, black holes are natural time machines, pushing the limits of what we know about reality. In the next segment, we'll dive deeper into the history of black holes, how scientists first imagined them, what early explorers like John Michel and Carl Schwarzschild predicted, and how the idea went from wild speculation to the cutting edge of physics. We'll see how black holes changed our understanding of space, time, and the very nature of existence. Stay tuned. The most mind-bending revelations are still ahead. The story of black holes begins long before anyone had the tools to find them. Imagine it's the late 1700s, long before Einstein, before the idea of space-time even existed. In England, a scientist named John Michell makes a bold prediction. He wonders, what if there were stars so massive, with gravity so strong, that not even light could escape their pull? He calls them dark stars, and the idea is so radical that it's mostly forgotten for over a century. Then, in 1915, Albert Einstein changes the game. With his theory of general relativity, he shows that gravity is not just a force, but a bending of space and time itself. Suddenly, the universe is no longer a static stage, but a flexible fabric that can curve, stretch, or even tear. Just a year later, Carl Schwarzschild, a German physicist, solves Einstein's equations for a point mass, essentially the math for a black hole. His solution describes a place where space and time curve infinitely, where the event horizon marks a point of no return. But for decades, most scientists think black holes are just a mathematical oddity, a curiosity, not something that could exist in reality. The idea seems too extreme. What could possibly squeeze so much matter into such a tiny space? It takes time, new evidence, and a few scientific rebels to shift the paradigm. In the 1960s, the field explodes. Astronomers detect strange signals from space, quasars, pulsars, X-ray binaries. These cosmic beacons point to something massive and invisible, something that fits the description of a black hole. The evidence piles up, stars orbiting an unseen companion, powerful jets of energy shooting from the hearts of galaxies, gravitational waves echoing across the cosmos. Suddenly, black holes are no longer theoretical. They're real, and they're everywhere. Now let's turn to what makes black holes so bizarre: the singularity. This is the heart of the black hole, the place where all our understanding breaks down. Here, the laws of physics as we know them no longer apply. Time and space become infinitely curved. Some theories suggest the singularity could even be a bridge to another universe, or a seed for a new Big Bang. The truth? Nobody knows. It's a cosmic mystery at the edge of science. Black holes come in many forms. There are stellar mass black holes, created when massive stars run out of fuel and collapse. There are supermassive black holes, millions or billions of times heavier than the Sun, lurking at the center of galaxies, including our own Milky Way. How these giants form is still an open question. Did they start as small black holes that grew by swallowing stars and gas? Or did they form in the early universe, born big from the very start? And then, there are the strangest black holes of all. Primordial black holes, hypothetical objects that may have formed just after the Big Bang itself. If they exist, they could answer questions about dark matter, galaxy formation, and even the fate of the universe. But let's bring it back to time travel. To understand how black holes might unlock this ultimate dream, we need to dive into the concept of space-time. In Einstein's universe, space and time are not separate. They're woven together into a single, four-dimensional fabric. Mass and energy curve this fabric, and the stronger the gravity, the more intense the distortion. Near a black hole, this distortion becomes extreme. Time slows down so much that for someone hovering just outside the event horizon, years could pass outside while only minutes go by for them. This isn't just theory. It's been demonstrated in movies like Interstellar, but it's also a consequence of real physics. In fact, astronauts on the International Space Station age slightly less than people on Earth due to time dilation, though the effect is tiny. But what if we could use a black hole's time-warping properties to travel into the future? In theory, if you could orbit close to the event horizon, then return to safety, you would find that more time has passed in the outside universe than for you, a real form of time travel to the future. The closer you get to the event horizon, the greater the time difference. The idea of going back in time is even stranger. Some solutions to Einstein's equations, like rotating, Kerr, black holes, suggest the possibility of closed time-like curves, loops in space-time that could, in theory, allow time travel to the past. These ideas are highly speculative and come with huge paradoxes, like the famous grandfather paradox, where changing the past could make the present impossible. Still, the universe doesn't forbid these scenarios outright, at least not yet. Some physicists propose that quantum effects or cosmic censorship may prevent time machines from forming. Others wonder if nature hides such paths behind horizons that can never be crossed. So, are black holes really time machines? Or are they simply nature's way of hiding its deepest secrets? In the next segment, we'll explore the most mind-bending theories, wormholes, Einstein-Rosen bridges, and how the fabric of space itself might fold to create shortcuts through time. We'll also look at the evidence, what astronomers have seen, what's still speculation, and why the next discovery could change everything. Stay with us. The real adventure is just beginning. The idea of wormholes has fascinated scientists and science fiction writers for generations. Imagine a tunnel through space-time, a shortcut that could connect two distant places, or even two different times. In theory, wormholes are possible solutions to Einstein's equations. The simplest kind is the Einstein-Rosen bridge, a mathematical model describing two black holes connected by a tunnel. But there's a catch. In most models, these bridges collapse too quickly for anything to pass through. Still, the allure of wormholes is irresistible. They capture the imagination because they offer hope, the hope that the universe is more flexible, more interconnected than it seems. If a wormhole could be stabilized, kept open by some form of exotic matter with negative energy, it might, in theory, allow travel not just across space, but across time. Enter the realm of closed time-like curves and time loops. These are paths through space-time that circle back on themselves, allowing you to revisit the past. But before you start building a time machine, there are problems. First, nobody knows if exotic matter exists in the amounts needed. Second, even if a wormhole could be created, it would be incredibly unstable. The slightest disturbance, like a stray photon, could collapse it instantly. And there's the risk of paradoxes. What happens if someone goes back and changes history? Would the universe protect itself from such changes? Or would new timelines branch off, creating parallel worlds? Physicists like Kip Thorne have explored these questions, working out the math and even consulting on Hollywood films like Interstellar. Thorne's calculations show that time travel through a wormhole, while not forbidden by known physics, would require technologies and energies far beyond anything humanity can achieve right now. But science has a habit of surprising us. Let's come back to what we know. Black holes themselves can be detected not by what they emit, but by what they affect. We spot them by the way they bend the paths of nearby stars, by the X-rays released as matter spirals into their grasp, and most recently, by the gravitational waves they create when they collide. In 2015, LIGO detected ripples in space-time from two merging black holes, confirming Einstein's predictions and opening a new window into the universe. One of the most stunning achievements in recent years was the Event Horizon Telescope's image of a black hole's shadow in the galaxy M87. This image showed the dark outline where light is swallowed and revealed the swirling ring of hot plasma surrounding the event horizon. For the first time, humanity had a picture of the unseeable, a direct glimpse into a realm where space and time are twisted beyond recognition. This evidence tells us black holes are real, powerful, and common. But it also teases us with new mysteries. The singularity at the center is hidden behind the event horizon, protected from direct observation. What actually happens inside? Does the information carried by matter and energy truly vanish? Or is it preserved in ways we don't yet understand? This is the heart of the black hole information paradox, a puzzle that links quantum physics and gravity. The paradox goes like this. Quantum theory says information cannot be destroyed. But if a black hole swallows matter and then eventually evaporates via Hawking radiation, where does the information go? Stephen Hawking himself wrestled with this question for decades. Some think information might leak out in a scrambled form. Others believe the universe has ways of preserving every bit of data, perhaps on the event horizon itself, like a hologram. This is where the concept of the holographic principle enters. In this wild idea, everything that falls into a black hole is somehow encoded on its surface, not lost inside. If true, this would mean the universe is more like a vast cosmic computer, storing every detail on its edges. It's a mind-bending notion, and it might just be the link between gravity, quantum mechanics, and the true nature of reality. So, what does this have to do with time travel? The closer we look at black holes, the more we realize that their secrets could be the key to uniting the two great theories of physics: general relativity, which governs the very large, and quantum mechanics, which rules the very small. Time travel, if it's possible, will be found in the place where these two realms overlap. But we're not there yet. Our best telescopes and computers are only beginning to scratch the surface. Every answer leads to more questions, and every discovery pulls us deeper into the mystery. Still, humanity is relentless in its curiosity. In the next segment, we'll explore how black holes are formed in the chaos of dying stars, what happens in the moments just before and after collapse, and why the birth of a black hole may be the most dramatic event in the universe. We'll look at the supernovae that light up galaxies, the gamma-ray bursts that announce the death of giants, and the echoes they leave across time and space. Time travel's secret might be locked away in the furnace of a collapsing star. Let's go there next. To witness the creation of a black hole is to watch the universe at its most violent and transformative. The process begins with a star, many times heavier than our sun, running out of nuclear fuel. For millions of years, it has burned hydrogen and helium in its core, balancing the outward pressure of fusion against the inward pull of gravity. But eventually, the fuel runs out. Gravity wins. What happens next is one of the most cataclysmic events in nature: a supernova. The core collapses in a fraction of a second, crushing matter into an unimaginably dense state. The outer layers are blasted outward, shining so brightly that for days or weeks, a single supernova can outshine an entire galaxy. The light, neutrinos, and shockwaves travel across space, carrying the news of a star's death to every corner of the universe. At the heart of the explosion, if the remaining mass is great enough, nothing can stop the collapse. Protons and electrons merge into neutrons, creating a neutron star, a city-sized object with the mass of our sun. But if the core is even heavier, gravity crushes everything down to a singularity. The event horizon forms, and a black hole is born. These births are rare, but they shape galaxies. The elements forged in supernova, gold, silver, uranium, even the iron in your blood, are scattered across the cosmos, seeding future generations of stars and planets. In this way, black holes are not just destroyers, they're creators too, recycling matter and energy through cosmic time. But the story doesn't end there. As black holes feed on gas and stars, they grow. Some become the engines of active galaxies, blasting out jets of particles at nearly the speed of light. These jets, powered by twisting magnetic fields and spinning disks of matter, can extend for thousands of light years, shaping the structure of entire galaxies. In the centers of some galaxies, supermassive black holes slumber, waking now and then to unleash furious outbursts that can affect millions of stars. What's it like to approach a black hole? Let's imagine. As you get closer, the light from the universe behind you is stretched and warped. Colors shift toward red, then fade to darkness. The sky above seems to swirl, and time slows. The tidal forces, differences in gravity from head to toe, become so strong they would stretch and compress your body in a process known as spaghettification. No human could survive this journey, but the physics is real and has been simulated in powerful computers. From a distance, a black hole's gravity bends starlight into strange rings and arcs. Astronomers call this gravitational lensing, and it allows us to see galaxies that would otherwise be hidden. This bending of light, predicted by Einstein and confirmed by observation, is one of the ways we know black holes are out there. But black holes aren't just in distant galaxies. There are likely millions in our own Milky Way. Some wander alone, invisible except when they interact with other stars. Others are in binary systems, feeding on their companions and lighting up the sky with X-rays. One of the best studied is Cygnus X1, a black hole about 6,000 light-years away, discovered by the way it pulls matter from a blue supergiant star. Our own galaxy has a supermassive black hole at its heart, Sagittarius A. With a mass of over 4 million suns, it sits in a crowded region of space, surrounded by swirling stars and clouds of gas. In 2022, astronomers released the first direct image of its shadow, confirming predictions made decades before. Now, let's return to time travel. The intense gravity near a black hole warps space-time to such a degree that it's as if the rules of the universe are rewritten. Time dilation becomes so extreme that theoretically, you could watch the universe's future unfold in fast forward. A few minutes spent near the event horizon could mean thousands or millions of years pass in the rest of the cosmos. In this sense, black holes are natural fast-forward buttons for time. But what about going backward? The idea of using black holes to travel to the past is still wrapped in paradox and uncertainty. Some physicists propose that if a black hole is rotating, its space-time might twist in such a way as to allow closed time-like curves, loops in time. But these paths are fraught with instability and may not exist in the real universe. Other theories suggest that quantum effects, or the presence of matter, would destroy any hope of a usable time machine. Yet black holes remain our best laboratory for testing the limits of physics. They challenge us to think bigger, to question what we know about reality, and to keep searching for connections between gravity, quantum mechanics, and the flow of time. In the next segment, we'll explore the quest to unify physics, the wildest ideas about the true nature of black holes, and how solving these mysteries might bring us closer than ever to understanding time travel itself. Don't look away. The next revelation could change the way you see the universe forever. Physicists have spent decades trying to reconcile general relativity, the theory that explains black holes and gravity, with quantum mechanics, which governs the world of atoms and particles. Black holes sit at the crossroads of these two realms, challenging us to create a theory of everything. This quest has led to some of the most daring and imaginative ideas in science. String theory is one such idea. It proposes that all matter and forces are made of tiny vibrating strings of energy, far smaller than any particle we've observed. In this framework, black holes might not have singularities at their centers, but instead incredibly dense string balls, where the fabric of space and time is knotted in complex ways. This could resolve some of the paradoxes of black holes, like what happens to information when it falls in. But much of this theory remains untested. Another bold concept is loop quantum gravity. Here, space itself is made of tiny loops, woven together in a cosmic tapestry. If this is true, then black holes might not destroy information after all. Instead, the core could bounce at the end of its life, spewing out everything it swallowed in a sort of cosmic rebirth. These ideas push the limits of imagination, but they are rooted in real mathematics and serious physics. One of the most tantalizing connections between black holes and time travel comes from the idea of quantum entanglement. In this phenomenon, two particles become linked so that the state of one instantly affects the other, no matter how far apart they are. Some physicists speculate that black holes could be connected by wormholes, essentially shortcuts in space-time created by entanglement. This ER-EPR conjecture, named after Einstein-Rosen bridges and Einstein-Podolsky-Rosen paradox, suggests that Let's not forget the mysteries of Hawking radiation. In the 1970s, Stephen Hawking showed that black holes aren't completely black. They emit a faint glow due to quantum effects near the event horizon. Over time, this radiation causes black holes to shrink and eventually evaporate. But as they vanish, what happens to the information inside? Does it escape with the radiation, or is it lost forever? This is the famous information paradox, and it sits at the heart of the quest to unify physics. Some theorists propose that information is encoded on the event horizon itself, a two-dimensional surface that stores all the details of what fell in. This idea is known as the holographic principle, and it has profound implications. It suggests that our entire universe could be described as a kind of hologram, with reality projected from a distant, lower dimensional boundary. The implications for time travel are subtle but profound. If the information about everything that happens near a black hole is never truly lost, then the flow of time, even in the most extreme environments, is subject to deep laws we are only beginning to uncover. Perhaps the secret to time travel is hidden in the way information and causality are woven together at the edge of a black hole. Let's look at what this means for our understanding of reality. The universe is not a clockwork machine ticking forward predictably. It's a dynamic, evolving network of events, where past, present, and future are linked in ways that may defy common sense. Black holes teach us to question our assumptions, to wonder if time itself could have loops, shortcuts, or hidden dimensions waiting to be discovered. Yet for all these mind-bending theories, black holes remain stubbornly real. They collide, merge, and grow, shaping galaxies and lighting up the universe with bursts of energy. They are cosmic laboratories where the extremes of physics play out, and where every new observation brings us closer to the edge of the unknown. Let's not lose sight of the human side. The quest to understand black holes and time travel is a deeply human story. It's about curiosity, courage, and the drive to explore the impossible. From John Michel's Dark Stars to the first picture of a black hole's shadow, every discovery is a testament to the power of imagination. In the next segment, we'll visit the frontiers of observation, the telescopes, detectors, and simulations that let us see black holes, track their dances, and glimpse the signatures of time's strangest tricks. We'll meet the people behind the discoveries and learn how a new era of exploration is unfolding right now, one that might finally reveal the true connection between black holes and time travel. To unlock the secrets of black holes and their link to time, scientists use some of the most advanced tools ever built. Ground-based telescopes like the Very Large Telescope in Chile and space observatories such as Hubble and Chandra allow astronomers to study black holes across the electromagnetic spectrum. But seeing a black hole directly is impossible. They emit no light. Instead, astronomers detect their presence by watching the behavior of nearby stars and gas. One breakthrough came from watching stars at the heart of our own Milky Way. Over decades, astronomers observed these stars following tight, fast orbits around an invisible point, evidence of a supermassive black hole, Sagittarius AI. The movement was so precise, it won Reinhard Genzel and Andrea Ghez the Nobel Prize in Physics in 2020. These observations gave us our first solid proof that supermassive black holes are real, not just theoretical. But what about the dynamics of black holes themselves? In recent years, astronomers have detected gravitational waves, ripples in the fabric of space-time created by the collision and merger of black holes. Instruments like LIGO and Virgo have picked up these waves, letting us listen to the universe in a new way. Each wave carries information about the masses, spins, and locations of merging black holes, giving us new clues about how they form and grow. Supercomputers play a key role in simulating black holes. By modeling the collapse of stars, the collision of black holes, and the behavior of matter near the event horizon, scientists can test theories that are impossible to recreate in a lab. These simulations help us visualize how space-time is stretched and twisted, and what an observer might experience near a black hole. Let's not forget the Event Horizon Telescope, EHT, a global network of radio telescopes that work together to create an Earth-sized virtual observatory. In 2019, the EHT team released the first-ever image of a black hole's shadow in the galaxy M87, a feat that required atomic clock precision and petabytes of data. This image confirmed decades of predictions and showed that even the wildest ideas of Einstein's theory hold up in the real universe. These observations and simulations also test the boundaries of time travel theories. For instance, if closed time-like curves or wormholes existed, they might leave subtle imprints in the patterns of light and gravity around black holes. Astronomers scour data for these signatures, hoping to spot a clue that reality is stranger than we imagine. But black holes are not just the domain of physicists and astronomers. Artists, writers, and filmmakers are captivated by their mysteries. Movies like Interstellar and the Black Hole, novels like Stephen Baxter's Time, and countless comics and games imagine black holes as portals to other dimensions, eras, or universes. While these stories often take creative liberties, they reflect a deep truth. Black holes ignite our sense of wonder and make us ask the biggest questions about existence. The search for black holes and their connection to time travel is also inspiring a new generation of scientists. Students design experiments, analyze telescope data, and run computer simulations. Citizen scientists help classify black hole candidates or find gravitational lensing events in survey images. The boundaries between professional and amateur, between science and storytelling, are blurring. Let's pause for a moment and consider. Every discovery we make about black holes reshapes our view of reality. We once thought the universe was calm, eternal, and unchanging. Now we know it's a place of constant transformation, where matter and energy can vanish, reappear, and bend in ways we never thought possible. Black holes are at the heart of this revolution. As we move forward, the tools will only get better. Next-generation observatories like the James Webb Space Telescope, the Laser Interferometer Space Antenna, LISA, and ever more powerful computers promise even deeper insights. The mysteries of black holes and their role in time travel may soon move from speculation to observation. In the next segment, we'll explore how these cosmic enigmas inspire not just science, but philosophy and art. We'll dive into the cultural legacy of black holes, the myths and metaphors they generate, and why the quest to understand them is ultimately a quest to understand ourselves, our fears, and our dreams. Stay curious. There's more to uncover. The fascination with black holes isn't limited to observatories or physics labs. These cosmic mysteries have become powerful symbols in our culture, shaping how we think about the unknown, our own mortality, and the possibility of transcending limits. To artists and storytellers, black holes represent portals, traps, and even mirrors for the soul, a place where everything familiar vanishes and something new might emerge. From the earliest science fiction, writers have used black holes to explore the edges of human experience. In the 1960s and 70s, as black holes moved from obscure theory to astronomical reality, stories like Arthur C. Clarke's The Star and movies such as Disney's The Black Hole brought these objects into popular imagination. Some tales use black holes as doomsday devices, swallowing planets and civilizations. Others turn them into gateways for interstellar travel, or as metaphors for the mind's deeps. This cultural legacy isn't just fiction. Black holes challenge philosophers to ask, what does it mean for something to disappear forever? Can information truly be lost? Is there a fundamental boundary to knowledge? Or do the secrets of black holes hint at deeper connections between mind, matter, and meaning? These questions echo in poetry, art, and philosophy, each field searching for its own language to express the awe and terror of the unknown. Musicians have even composed symphonies inspired by black holes, weaving together the themes of loss, transformation, and rebirth. Visual artists imagine what the inside of a black hole could look like, painting swirling vortices or cosmic tunnels. In classrooms, teachers use the drama of black holes to ignite curiosity, encouraging students to ask questions that push beyond the textbook. Black holes also serve as metaphors for human experience. We all encounter events that seem inescapable, moments of crisis, loss, or radical change. Like a star collapsing into a singularity, our lives can be reshaped in an instant. But just as matter falling into a black hole may one day re-emerge as Hawking radiation, so too can new possibilities arise from even the darkest experiences. Black holes teach us about humility and hope. The intersection of science, art, and philosophy around black holes has another effect. It democratizes the mystery. You don't have to be a physicist to wonder what lies beyond the event horizon, or to imagine traveling through time. This shared curiosity binds us together as explorers, each following our own path to the edge of the unknown. At the same time, black holes remind us of the limits of our knowledge. The cosmic censorship conjecture, proposed by Roger Penrose, suggests that singularities are always hidden from view by event horizons, protecting the universe from paradoxes and chaos. Yet some solutions to Einstein's equations, like naked singularities, suggest there could be regions where the rules break down and anything is possible. This tension between order and chaos, knowledge and mystery, gives black holes their enduring power. They are both subjects of rigorous scientific study and icons of the imagination. Each new discovery blurs the line between what is real and what is possible. As we continue, let's consider the human drive to reach beyond the event horizon, both literally and metaphorically. What pushes scientists to chase after data that may never be complete, or writers to invent worlds that bend the laws of nature? At its heart, the quest to understand black holes and time travel is about hope, a belief that the universe still holds surprises and that the future is open. In the next segment, we'll bring all these threads together, exploring how new discoveries about black holes are changing our view of time, destiny, and what it means to be part of a universe where the impossible may someday become reality. Get ready to see the big picture, because we're heading for the final horizon. Every new discovery about black holes seems to ripple outward, changing how we think about not just physics, but about the flow of time and our place in the universe. Consider what it means to live in a cosmos where time itself can bend, loop, and possibly even connect past and future through hidden tunnels. For centuries, people assumed time was absolute, a river flowing from the past, through the present, into the future. Black holes shattered that certainty. We've seen how time slows near a black hole, and how the very shape of reality is warped by gravity. We've explored the wildest ideas: wormholes, cosmic strings, closed time-like curves, and the possibility that information might persist even after crossing the event horizon. These ideas force us to rethink everything we thought we knew about causality and fate. But these discoveries also challenge us to accept uncertainty. The closer scientists look at black holes, the more the answers slip away, transformed by quantum fuzziness, chaos, and the unknowable details of singularities. In this way, black holes become a metaphor for the future itself, always beckoning, always mysterious, always just beyond our reach. Yet hope persists. Every year, new technology and creativity bring us closer to understanding. Gravitational wave detectors pick up the faint tremors of distant collisions, while artificial intelligence combs through mountains of data for subtle patterns. Supercomputers render the swirling gas and light around black holes with unprecedented clarity, testing theory against observation. This pursuit has global reach. Scientists on every continent collaborate in real time, sharing findings and building tools that no one nation could achieve alone. From Chilean mountaintops to South African deserts, from spacecraft in orbit to remote Antarctic stations, the quest to unlock the secrets of black holes unites humanity in a cosmic project. What then do these efforts teach us about time travel? For now, practical journeys into the past or future remain out of reach. But the physics is clear. Black holes are nature's ultimate time machines, warping reality in ways that, under the right circumstances, could allow time to fold back on itself. Even if we never build a real time machine, the insights gained from studying black holes may revolutionize our understanding of memory, destiny, and free will. Let's reflect on the journey so far. We've moved from the earliest speculation about dark stars to Nobel Prize-winning observations, from the math of singularities to the images of shadowy event horizons. Along the way, we've faced paradoxes and possibilities, each one forcing us to confront the limits of human knowledge. As this exploration nears its final chapters, we must ask, what new discoveries will tomorrow bring? Could new physics, perhaps a quantum theory of gravity, unlock time travel's secrets? Will the first human-made probe ever cross an event horizon? Or will we find that some mysteries are forever out of reach? One thing is certain: the quest continues. Every time a black hole merges, a star explodes, or a scientist dreams, we move closer to answers. The boundary between science fiction and science fact is thinner than ever, and the next leap forward could come from anywhere: a high school classroom, a remote observatory, or a mind lost in wonder at the stars. In our next segment, we'll draw these ideas together, looking at how black holes and the search for time travel reshape our sense of meaning, purpose, and the grand adventure of existence. We'll ask not just what is possible, but what kind of universe we hope to inhabit. The horizon is close. Let's take one more step toward it. We are nearing the end of our journey, standing on the threshold of the known and the unknown. The search for answers about black holes and time travel has brought us face to face with the universe's deepest mysteries and our own relentless curiosity. What have we learned, and where do we go from here? First, we've discovered that black holes are not just cosmic monsters or plot devices, but the engines of creativity and transformation. They shape galaxies, birth elements, and connect the smallest scales of reality with the largest. Through them, we glimpse the unity of the universe, a cosmos where time and space are forever dancing, forever intertwined. Second, the pursuit of time travel isn't just about building a machine or finding a wormhole. It's about the desire to understand how reality works, to stretch the boundaries of possibility, and to imagine a world where the past and future might meet. In this quest, black holes are our teachers, showing us both the limits of what we know and the directions we might explore next. The mysteries we face are profound. What lies inside a singularity? Can information ever truly be lost? Are wormholes real? And if so, could they ever be stabilized or traversed? These questions push the frontiers of physics, demanding new theories and technologies. They also ask us to confront paradoxes of causality, of fate, of the very nature of existence. Let's reflect on the extraordinary progress made in just a few decades. Not long ago, black holes were dismissed as mathematical oddities. Today, they are observed, measured, and photographed. Time travel has moved from myth to mathematics, with real equations describing scenarios that once belonged only to dreamers. The journey from fiction to fact is ongoing, and every generation builds on the daring of those before. Yet this journey isn't just for scientists. The fascination with black holes and time travel belongs to everyone. Whether you're watching the stars, running a simulation, or reading a story that stretches your imagination, you are part of humanity's quest to understand its place in the cosmos. Black holes invite us all to ask bigger questions, to challenge our limits, and to never stop wondering. So, what's next? The search for a theory of everything continues, bridging the gap between gravity and quantum mechanics. New observatories and collaborations will probe deeper, measure finer details, and bring the mysteries of black holes into sharper focus. Perhaps, someday, an answer to time travel's riddle will emerge, not as a magical device, but as a deeper understanding of the universe's fabric. Before we conclude, let's remember that the real power of black holes and time travel lies in what they reveal about us. They remind us that the unknown is not a barrier, but a frontier, that every limit is a challenge, and every mystery is an invitation. In facing the darkness, we discover our own capacity for light, imagination, and hope. As we prepare for our final thoughts, take a moment to look up at the night sky, or to close your eyes and picture the swirling darkness at the heart of a galaxy. Let that sense of awe settle in. We live in a universe stranger and more wondrous than anyone could have imagined. In the final segment, we'll recap our key discoveries, leave you with one last message to ponder, and invite you to carry the adventure forward into your own questions, your own dreams, and your own explorations of space and time. Our voyage into black holes and the secrets of time travel is coming to a close. But endings in science are just new beginnings. fresh questions, deeper wonder, and a promise that the journey never truly stops. Let's gather the threads of what we've explored and look forward to what might come next. We began with a question. Could black holes hold the secret to time travel? Along the way, we've discovered singularities, event horizons, wormholes, and the staggering power of gravity to bend reality itself. We've seen how black holes challenge our understanding of space and time, and how their study unites physics, philosophy, and imagination in a grand cosmic project. We've explored the wildest possibilities, closed time-like curves, the holographic principle, Hawking radiation, and quantum entanglement. We've celebrated the triumphs of technology, from the Event Horizon Telescope to the detection of gravitational waves. We've also met the challenges, paradoxes, unanswered questions, and mysteries that will inspire generations of explorers. Most of all, we've learned that black holes are not obstacles, but opportunities. They are cosmic laboratories where the laws of nature are pushed to their limits and sometimes rewritten. They remind us that the universe is alive with possibility, and that we are part of a never-ending story. Time travel, whether it ever becomes practical or remains a dream, is above all a question about what kind of future we can imagine. The universe is not static. It's full of doors waiting to be opened. With every discovery, every observation, every act of curiosity, we move closer to understanding who we are, where we come from, and where we might go. So, what will you take with you from this journey? Maybe it's a new appreciation for the stars and the depths that surround them. Maybe it's a sense of wonder, or a question you can't shake. Maybe it's the realization that the biggest mysteries are not always out there, but within ourselves. Let this story inspire you to keep exploring, whether through science, art, or your own dreams. If you enjoyed this journey, consider subscribing, sharing, or joining the conversation. Ask your questions, make your discoveries, and never stop imagining what lies beyond the next horizon. The universe is vast. Its secrets are waiting. Time, as black holes remind us, is never as simple as it seems. The adventure is yours. Thank you for watching, listening, or imagining with us. Until next time, keep your mind open, your curiosity sharp, and your sense of wonder alive. What would you do if you could travel through time? We are nearing the end of our journey, standing on the threshold of the known and the unknown. The search for answers about black holes and time travel has brought us face to face with the universe's deepest mysteries and our own relentless curiosity. What have we learned, and where do we go from here? First, we've discovered that black holes are not just cosmic monsters or plot devices, but the engines of creativity and transformation. They shape galaxies, birth elements, and connect the smallest scales of reality with the largest. Through them, we glimpse the unity of the universe, a cosmos where time and space are forever dancing, forever intertwined. Second, the pursuit of time travel isn't just about building a machine or finding a wormhole. It's about the desire to understand how reality works, to stretch the boundaries of possibility, and to imagine a world where the past and future might meet. In this quest, black holes are our teachers, showing us both the limits of what we know and the directions we might explore next. The mysteries we face are profound. What lies inside a singularity? Can information ever truly be lost? Are wormholes real? And if so, could they ever be stabilized or traversed? These questions push the frontiers of physics, demanding new theories and technologies. They also ask us to confront paradoxes of causality, of fate, of the very nature of existence. Let's reflect on the extraordinary progress made in just a few decades. Not long ago, black holes were dismissed as mathematical oddities. Today, they are observed, measured, and photographed. Time travel has moved from myth to mathematics, with real equations describing scenarios that once belonged only to dreamers. The journey from fiction to fact is ongoing, and every generation builds on the daring of those before. Yet this journey isn't just for scientists. The fascination with black holes and time travel belongs to everyone. Whether you're watching the stars, running a simulation, or reading a story that stretches your imagination, you are part of humanity's quest to understand its place in the cosmos. Black holes invite us all to ask bigger questions, to challenge our limits, and to never stop wondering. So, what's next? The search for a theory of everything continues, bridging the gap between gravity and quantum mechanics. New observatories and collaborations will probe deeper, measure finer details, and bring the mysteries of black holes into sharper focus. Perhaps, someday, an answer to time travel's riddle will emerge, not as a magical device, but as a deeper understanding of the universe's fabric. Before we conclude, let's remember that the real power of black holes and time travel lies in what they reveal about us. They remind us that the unknown is not a barrier, but a frontier, that every limit is a challenge, and every mystery is an invitation. In facing the darkness, we discover our own capacity for light, imagination, and hope. As we prepare for our final thoughts, take a moment to look up at the night sky, or to close your eyes and picture the swirling darkness at the heart of a galaxy. Let that sense of awe settle in. We live in a universe stranger and more wondrous than anyone could have imagined. In the final segment, we'll recap our key discoveries, leave you with one last message to ponder, and invite you to carry the adventure forward into your own questions, your own dreams, and your own explorations of space and time. Our voyage into black holes and the secrets of time travel is coming to a close. But endings in science are just new beginnings, fresh questions, deeper wonder, and a promise that the journey never truly stops. Let's gather the threads of what we've explored and look forward to what might come next. We began with a question. Could black holes hold the secret to time travel? Along the way, we've discovered singularities, event horizons, wormholes, and the staggering power of gravity to bend reality itself. We've seen how black holes challenge our understanding of space and time, and how their study unites physics, philosophy, and imagination in a grand cosmic project. We've explored the wildest possibilities, closed time-like curves, the holographic principle, Hawking radiation, and quantum entanglement. We've celebrated the triumphs of technology, from the Event Horizon Telescope to the detection of gravitational waves. We've also met the challenges, paradoxes, unanswered questions, and mysteries that will inspire generations of explorers. Most of all, we've learned that black holes are not obstacles, but opportunities. They are cosmic laboratories where the laws of nature are pushed to their limits and sometimes rewritten. They remind us that the universe is alive with possibility, and that we are part of a never-ending story. Time travel, whether it ever becomes practical or remains a dream, is above all a question about what kind of future we can imagine. The universe is not static. It's full of doors waiting to be opened. With every discovery, every observation, every act of curiosity, we move closer to understanding who we are, where we come from, and where we might go. So, what will you take with you from this journey? Maybe it's a new appreciation for the stars and the depths that surround them. Maybe it's a sense of wonder, or a question you can't shake. Maybe it's the realization that the biggest mysteries are not always out there, but within ourselves. Let this story inspire you to keep exploring, whether through science, art, or your own dreams. If you enjoyed this journey, consider subscribing, sharing, or joining the conversation. Ask your questions, make your discoveries, and never stop imagining what lies beyond the next horizon. The universe is vast. Its secrets are waiting. Time, as black holes remind us, is never as simple as it seems. The adventure is yours. Thank you for watching, listening, or imagining with us. Until next time, keep your mind open, your curiosity sharp, and your sense of wonder alive. What would you do if you could travel through time?